In this video we will be doing chapters 9, sections 8 through 11. There is some information in here that I'm going to leave the slides up for that we won't be going into as much deep depth in class or in tests and quizzes. Some of it will show up in the homework, so we'll talk about it briefly, but we might be skipping around a little bit. So in this section, we'll be spending a great amount of time on salts, as well as strength of acids and bases. We touched upon this concept in our acids and bases chapter, as well as when we did our solutions and we were talking about strong and weak electrolytes and what it means to be a strong acid or a strong base, or a weak acid and a weak base. Like I said, sections 10 and 11 will be just briefly talked about so that we can kind of prepare you for some of the things you may see in homework, as well as a lab that will be coming up. So the first thing we're going to discuss is a salt. So up until now, we've tried to be really make a good distinction between table salt, NaCl, and the general term salt. In chemistry, the term salt is more than NaCl. In fact, NaCl is a type of salt, but is not the only type of salt that there is. A salt refers to a solid that's crystalline, and it's an ionic compound that will be solid at room temperature. We know that ionic compounds must have a cation and an anion to them. So pretty much all the ionic compounds that are solids that we've talked about, those are going to be considered salts. The cation of a salt can be any positive ion except for H+. We know that when we have H+, like in HCl, right, then we had an acid. So remember, an inorganic compound, an ionic compound, has the recipe of a metal and a nonmetal. We can also have something like a polyatomic ion. That would be acceptable as well. So we know acids and metals, they make salts plus hydrogen gas. Acids and metal oxides make salts and water. Metal hydroxides and salts make salt and water, usually in greater combination, so like maybe 2 moles of water. Acids and metal carbonates make salt, CO2, and water, and so same with bicarbonates. So again, we talked about this in the last video, and we did this with a series of acids with magnesium. So magnesium the metal, magnesium oxide, magnesium hydroxide, magnesium carbonate, magnesium bicarbonate. So this is the general kind of breakdown of that. When we evaporate water, right? Water, if we remove water as a solvent. So think about if I have NaCl, table salt, which is a type of inorganic salt, ionic salt, in water, right? Where water was a solvent. I could evaporate off the water and I would be left with my inorganic compound again. When we use the term hydrate, what we're talking about is a salt that contains a specific number of water molecules that are part of the crystalline solid. So a hydrate is a solid, not a liquid, not like a solution or anything like that. It just has water molecules sometimes trapped in the crystal structure. And what we can do sometimes is dry out or heat up that solid crystalline structure a little bit and get rid of some of that water and kind of let that evaporate out and get what we would call an anhydrous, which means no water containing ionic compound. The water of hydration is the water retained as a part of a solid crystalline structure of some salts. So sometimes the actual structure of the salt has some water molecules in it. So for example, when we see hydrates, they look like this when we write the formula. We would have calcium sulfate monohydrate, which means we have one water molecule kind of bound to this overall solid compound. This is part of what makes things like casts and molds and things like that. Another one that we see a lot is, again, this is like a borax. I don't know if people use this still for their laundry, but it's like a powdered laundry soap. So like not a Tide Pod, but like a powdered laundry soap. And sodium tetraborate, and it's decahydrate, which means there are 10 waters associated around this crystal structure of this sodium tetraborate. So these are just examples for you to see what the hydrates look like. So this is kind of a long question to ask, but it's really good practice. Write equations for the representation and preparation of magnesium nitrate using the molecular equations to emphasize the salt formations. So magnesium, magnesium nitrate, right, where we're going to go through the different types of salts, right, with acid, all those different ones. So if you want to pause the video here and give that a shot, we will go through it, but I'll give you the opportunity to try this one on your own. So here we'll go through the different versions of it. So again, the goal here was the salt you would be creating would be this guy every time. So if we're going to have magnesium nitrate, our metal would have to be coming from some sort of magnesium, and our acid would have to have a nitrate in it. So nitric acid is a good option for that. So nitric acid plus the straight metal would just give us our desired salt plus hydrogen gas. If we had the oxide of that magnesium metal, we'd get our desired salt and water, right? So on and so forth, going through this process to get all the different types of salts. Well, it's the same salt, but all the different types of reactions that produce different materials. The amount of salt will produce 1 mole of positive or negative electrical charges, right, when dissolved or dissociated into its ions. So again, right, think about what we're looking at here. When we have this, when we know this is the secret language, right, this is an ionic compound, and it says aqueous. So that's the I know that you know that this is Mg plus 2 and 2 NO3 minuses. For a salt like NaCl, when it dissociates, right, remember dissociation, we get 1 Na plus ion for every 1 Cl minus ion. So 1 mole of salt produces 1 mole of the positive charge, or we could also say 1 mole of the negative charge. So that's an equivalent, right? 1 mole of NaCl equals 1 equivalent of NaCl plus. A salt like magnesium chloride, right, when that dissociates, we get 1 magnesium plus 2 ion and 2 of the Cl minus ions, right, because we have 2 of them. So 1 mole of salt produces 2 moles of positive charges. So 1 mole of salt equals 2 equivalents of the salt, or 1/2 the moles of the salt is to 1 mole of the equivalent. Determine the number of equivalents and milliequivalents. We won't really be doing milliequivalents on tests and quizzes. This may pop up in your homework, so just being aware of how it works is good. So when we look at KCl, we know that that's a 1-to-1 ratio. When we dissociate KCl, we get 1 mole of K plus and 1 mole of Cl minus broken up out of that. So if we have a 0.05 moles of the KCl, we would have 0.05 equivalents. And then to get the milliequivalents, we know that for every 1 equivalent, there would be 1,000 milliequivalents. Reaction between HNO3 and CaHCO3 will produce the same salt as the reaction between what? So in this case, we need to think about what this reaction would produce. This is a carbonate here with a metal, and this is an acid. So what happens to an acid and a metal carbonate? We will get our metal oxide, right, and our HNO3. These two things will produce this carbonate salt. We discussed strong versus weak acids and bases when we were talking about our electrolyte solutions in Chapter 7. So I'm just very briefly going to go through this again. Remember that our strong acids and bases, the definition for them is strong acids and bases dissociate 100%, right? So we get complete ionization. Weak acids and bases only partially dissociate. So here is just a chart to kind of give you some ideas of the difference between things that dissociate 100% and things that dissociate only kind of, and then things that hardly dissociate at all. So we have strong, moderate, and then weak. We don't say moderately strong because strong is determined by something that dissociates 100%. So we say they're moderately weak because they still dissociate a little bit, but not nearly close to 100%, but not nearly as bad as our weak ones. So when we're talking about acids, one thing we can talk about is, again, we're going to be talking in terms of the Bronsted definition of an acid. This would be something that gives up a hydrogen. There are three different kinds of acids that we'll primarily see. A monoprotic acid is a type of acid that can only give up one hydrogen. So an example for this would be HCl. We know that in HCl, there's only one H to give up, and that's it. A diprotic acid would be something like H2SO4. We could give up one hydrogen and have HSO4 minus, and then we could give up that second hydrogen and do another acid-base reaction to get SO4 minus 2. And then triprotic would be something that could give up three hydrogens. So here's some examples in terms of a monoprotic acid. Here's the acidic hydrogen here. Carbonic acid, we have two hydrogens. Formic acid and nitric acid, only one. Triprotic would be something like phosphoric acid, where we could give up all three of these hydrogens for acidic use. So ammonia is a weak base, most often encountered in addition to anions with strong acids. So here, oops, sorry, that should be a double arrow. So this should be the arrow pointing in that direction and in that direction. Sorry about that. So we have HNO3 plus H2O yielding H4 plus and OH minus. So if we were to go through this, we would know that this is a weak base, so it's only going to partially dissociate. So we're only going to have a little bit of this reaction going back and forth. NH3 is classified as a, we just said it, weak base, so only partially dissociate. When we are analyzing acids and bases, we know that we're going to be using pH as a good way to kind of describe the concentration of H plus in the solution, or maybe the concentration of OH minus in the solution. But really, how do we determine that is what we'll be talking about for the next few minutes. Now, I'm hopeful that we will be doing a virtual titration lab in a few weeks, so you will have some experience to kind of play around with doing a titration. So we aren't going to get into too much detail with this today, just to kind of give you the concept that this is a way in which we determine the concentrations or the molarities of unknown acids or bases. And we can do this because of an equivalence point. And this is often the point at which the unknown solution has the exact same amount as a known solution in terms of how it reacted. So basically we could say, ooh, okay, when I have this much of this material of an unknown acid or base, and it reacts in the same way as, 5 molar HCl, then I would know that I have a 5 molar solution. So we can go through and kind of use it as a way to compare a known to an unknown. Again, these are the techniques that we would use in a titration. I'm hopeful that we will have an opportunity to do an online kind of simulation of that, so I'm not going to go into too much detail with this right now. This won't be on any of the tests or quizzes. A titration question might show up in your homework, but I'm not too worried about that. One way we can also analyze different concentrations of our H plus ion in solution is by looking at pH, right? And we have indicators that change color depending on what the pH is. Another way we do this is with a pH meter, which is a little electrode that kind of monitors the concentration. So these are a little more precise oftentimes than something like our pH indicator colors. I'm going to skip the titrations calculation section for now. Please be aware that these slides are up, and that if when we do get to our titrations lab, that this will be a useful resource for you. This is the end of our third section. Like I said, the titrations portion of this will hopefully be done as part of a lab, so you'll be able to utilize these resources later on. But please be comfortable with what we talked about in terms of salts and strengths of acids and bases.